Um, okay. Today we're very happy to have Elisabetta Candellero from Roma 3 Universiteit,
Yeah.
who will be speaking to us about the coexistence in competing first package percolation, part 1, hyperbolic and non-amenable graphs. Thank you.
So thank you so much for inviting me to speak here. It's a great honor, great pleasure. So today I'll tell you something about you coexisting and competing first passage percolation. The first part, and then Tom will take over. And everything I'm going to tell you about today is based on joint works with Alexandre Stauffer. Right. So we start with the following. We're going to analyze a model for competing first passage percolation. So actually, we're going to deal with two first passage percolation processes. One is going to be denoted by FPP1, and the other one is going to be denoted by FPP lambda. And they're both going to spread on a graph G. So I will have pictures to describe the dynamics and everything, but just to fix the notation, to start with, we choose a graph G, which is going to be infinite, connected, and bounded degrees. So just think of your favorite graph with this kind of characteristics. We start by fixing two parameters. One of them is lambda, which is just going to be a positive number. And the other one is going to be a probability, and it's going to be denoted by P. So it's just going to be somewhere between 0 and 1. Now, I'll show you the pictures instead of reading these things, I'll just show you by pictures. So this model can be defined on basically any connected graph, and it works as follows. So imagine that here we're working on Z2 actually, and you choose a reference vertex. So let's say the origin. And what you do is you place a black particle at the origin. Then for every other vertex, which is not the origin, with probability P, which was this parameter here that you have chosen, independently for every vertex, you place a red particle, and you place no particle with probability 1 minus P. And as I said, you do this for every vertex other than the origin, independently. So you end up with a configuration like this. So this is your initial configuration. Just to, because I will use this name later on, just to say, so these initial red particles will be called seeds later on. And I guess it will be clear why this is true, why we call them like this. So as I said, this is your initial configuration. So how does the process work? Well, you start from your black particle, and from here you just you start with a first passage percolation process that spreads at rate 1. So what does that mean? Well, you just take all the edges which are adjacent to the origin, and you place on each of them independent exponential clocks that ring with rate 1. So you just wait for the first one to ring, and suppose it's this one. And if the next vertex is free, so if there is no particle there, then you declare it, you occupy it with a black particle. Okay, so you declare it black. In the meanwhile, these red guys here are sleeping. They are not moving, they're not doing anything. Okay, then now we have a slightly larger black cluster. And what we do, well, we continue in the following sense. So you take all edges adjacent to the current black cluster, and you place independent exponential clocks on each edge that rings with rate 1. So again, you just wait for the first edge to ring, for the first clock to ring. And again, suppose it's this one. If the next vertex is free, then you declare it black. So you occupy this vertex with a black particle. And you go on like this for a while. And in the meanwhile, as I said, the seeds, which are the red particles here, they're just sleeping. So you go on for a while. And at some point, what happens is that some edge will ring that will try to, in such a way that you will try to occupy a vertex which is already occupied by a seed, by a particle. So what happens here is that this seed here that was sleeping before is actually waking up. So it feels this perturbation and it wakes up. So we say here that we activate the seed. And what happens here is that this guy here starts spreading a first passage percolation that spreads with rate lambda. Lambda was the other parameter that you have chosen. So what happens here is just that on every edge adjacent to the current vertex, you place independent exponential clocks that ring with rate lambda. And again, you just wait for the first one to ring. And well, suppose it's this one here. And again, if the next vertex is free, this time you decorate it red. So here you have basically, let me just make a few remarks here. So here you have these two processes that are sort of these clusters here, the black made by the black process and the red process, they're sort of growing. And what we mean to say here is that they are competing for space. So the competition is in terms of space. Let me just say a couple of remarks here. So first of all, once a vertex turns black or turns red, then it will stay so forever. So if it turns black, then it will stay black forever. And if it turns red, then it will stay red forever. And moreover, in the picture that I had before, the seed was actually activated by a black particle. This doesn't need to be true, meaning that each seed can actually be activated by black or red particles, okay? So as I said, you're gonna get some cluster, like a growing cluster, which is very colorful. But so here, maybe it's a good moment to stop and ask if there is any question about this model, or if the model is clear.
Maybe I can ask, so
yeah, sure.
Can they move simultaneously, or let's say when red is activated, then black becomes dormant?
No, they can move simultaneously. Yes. Time is growing, and each edge is actually once you place an exponential clock on the edge, it just continues going until it rings, basically. And so these clusters actually, these two processes actually are growing simultaneously. That's correct. Yes.
Okay. Thank you.
No, thank you. Okay. So this is the model I will describe. So this is basically just a note for me to make sure I said everything. Right. So as I said, so you can think of these two processes: the black process that spreads at rate 1 and the red process that spreads at rate lambda. You can think of them as, for example, infections, and basically these processes, as I said, they are just competing for space. Now, in the following part of the talk, in the next part of the talk, I will actually discuss some very important concepts. So the first one is related to survival, and we say that FPP1 or respectively FPP lambda survives if the black process or respectively the red process occupies an infinite connected region of the graph when time goes to infinity. Okay, so this means survival. So if you get an infinite black cluster, we say that FPP1 survives. And if you get an infinite connected red cluster, then we say FPP lambda survives. And we talk about coexistence when both of them survive simultaneously. So if you get on the, when time goes to infinity, you can see simultaneously an infinite black cluster and an infinite connected red cluster. I see that maybe there's a question in the chat. I don't know if when red is activated, do the offspring of that activation also need to be activated by black ones? No, okay, so once you start spreading the red particles, then, I mean, red particles are keeping up, they're just, you just have first passage percolation that spreads at rate lambda. So the only thing that you need to activate is the seed. Once the seed is active, then FPP lambda starts spreading from there. So you don't need to activate every red offspring. So once you activate the seed, then the seed will start growing this FPP lambda, and it's going to be active automatically. So I hope I answered the question. Okay, so this process was actually introduced by Sidorovicius and Stauffer in a paper that actually appeared in Invenciones a few years ago. And the name they gave to this process was actually first passage percolation in hostile environment. And they introduced it on ZD, for D larger equal than 2, in order as an auxiliary model to understand what is called MDLA, which stands for multi-particle diffusion limited aggregation. And in some way, they discovered that by studying some properties of this particular model, they could deduce properties of this MDLA process, which is actually a very difficult process to analyze rigorously. However, I'm not going to discuss MDLA, but let's stick with the model I described. So in their paper, among many other results, they have this fact. So they show this fact, which is, so on ZD, for D larger equal than 2, obviously. So for every lambda between 0 and 1, so for every spread rate of the red process, but conditional on being, the spread rate has to be strictly smaller than 1, there is a critical value, P0, so that when P, the initial density of seeds, is strictly smaller than P0, then the probability that FPP1 survives and FPP lambda does not is strictly positive. So to be more specific, actually what they showed is the following. So FPP1 survives with positive, under these these conditions, FPP1 has positive probability of survival, and conditional on that event, so conditional on the event that FPP1 survives, then FPP lambda does not. And basically, just to have a picture in mind, this means that every red cluster that you start with, that you see in your graph, when the time goes to infinity, will be finite. So its size is not going to be bounded, because this is going to create a lot of problems in the proof, but the size is going to be finite almost surely. The size of every red cluster. I guess I can see another question. Is there only one black initially? How black number can reach infinity? Oh, what I meant to say here is that you get, so what you have here is that you start with one black particle, but this particle actually starts spreading this FPP1, this black process, first passage percolation that spreads at rate 1. And basically what is going to happen is that what happens is the FPP1 survives, is that you are going to see some sort of a very ramified cluster. So this is what you're going to see. I don't know if I answered, I hope I answered the question. In case I didn't, then just let me know.
No, sorry, branching process, but branching process starting from one particle. A number of the each particle can produce only four children, just the neighbors. So how it is possible to reach infinity?
Oh, okay. So sorry, let me go back to the pictures then. So maybe I will make this more clear. So what I meant to say in the initial part of the model is that, well, the thing is, you have your black cluster that is occupying all the neighbors. And the black cluster is trying to spread to the neighbors. But when time goes to infinity, this process will continue. So once you have this, for example, this black cluster here, well, obviously I didn't continue with the picture here, but what happens is you will have exponential clocks on all of that ring with rate 1 on every edge that is adjacent to the black cluster. Okay, so you basically keep, as time goes to infinity, what happens is that you keep spreading, trying to conquer more and more of the graph. So this is how you see the growth of this black process, which is an analog of what happens for the growth of the red clusters. They also grow using sort of the same dynamic. Once you activate the seed, they also grow with the same dynamic, just with a possibly different rate, because the red ones spread at rate lambda. Does that clarify the point?
Thank you.
Okay, good. Okay, let me go back. Okay, so right, so I was discussing roughly what happens on ZD, and actually Tom later on will discuss about some other very important properties, some other very important things that happen on ZD. So I strongly recommend to attend the next talk, which is going to be very nice and very interesting. Right, so here I have a few pictures where you get, so where the process is, you define the process on Z2, so we are in the same setting as before, and lambda is 0.7, and P assumes 3 different values according to the picture. So recall P was actually the initial density of seeds. So what you see here is the following. So the set of occupied vertices, let's stick, for example, to the first picture. The set of all occupied vertices is sort of this thing that looks like roughly like a circle, roughly. And what you see here that is colored actually represent the cluster up to that point occupied by FPP1. The different colors only represent the different epochs that are needed to FPP1 to actually occupy that region. And still looking at the first picture, you can see that there are some white things that look like holes. These kind of holes actually are clusters that are occupied by FPP lambda. Okay, so when the density of seed is really small, then you get this kind of behavior. So as I said, the colored cluster is the one occupied by FPP1. So as soon as you start increasing the density of seed, then you start looking at different pictures. So for example, this one at the right of the screen. So what you can see is that these kind of holes or these kind of regions, which are actually regions occupied by FPP lambda, are extremely large. And it's actually unclear, at least up to this point, it's actually unclear whether this, for example, this branch and this branch here are going to be connected as well, are going to connect themselves when time is, very, very large, or if they are going to be separated forever. For example, this is unclear. So this is just a few pictures, maybe to fix a bit the ideas about what this model does. Right, so far I have discussed a little bit what happens on ZD. But our setting is not actually ZD. So our setting is related to hyperbolic and non-amenable graphs. So let me just recall briefly first what hyperbolic graph means. So a hyperbolic graph is actually a shorthand to say a delta hyperbolic graph for some delta larger or equal than 0. And so a graph is delta hyperbolic if the following happens. So suppose to take any 3 vertices of the graph, which are x, y, and z, and just draw 2 geodesics, one going from x to z, and the other one going from x to y. And actually here, I want to make a remark saying that when I talk about geodesics, I mean with respect to the graph metric. So because we're looking at what happens on graphs. So this is just related to the graph metric. So so you draw 2 geodesics, one from x to z, the other one from x to y. And what you do is you cover these geodesics by balls of radius delta centered at the point, every point of these geodesics. Okay, so you obtain a picture like this. So I hope you can see that. And so the graph is said delta hyperbolic if every geodesic going from y to z is actually contained in the union of these balls here, the green balls that you see. So basically in the hyperbolic world, geodesic triangles are very, very thin, so are quite thin, so which means that geodesics are very close to each other. And this is actually a property that we need in the proofs, but we do believe that our results might be true also, not assuming this property, but for the proof, it's actually very important, for technically speaking, obviously. Right. So that was for hyperbolicity, whereas non-amenable graphs are graphs which are, well, in some way, in some texts, you see the definition saying that you get a graph is non-amenable when it has positive Chigger constant. So basically what this is saying is that there is a constant C, which just depends on the graph, so that the ratio between, for every finite set of vertices, if you consider the cardinality of the outer boundary of such set of vertices divided by the volume of the set, this is bounded from below by this constant C. So basically, what happens is that for every finite set of vertices, the cardinality of the outer boundary of such set and the cardinality of the set, meaning the volume, are roughly of the same order. So just to have a rough idea of what hyperbolic and non-amenable graphs are, just to have a couple of examples. So the one on the left is just an infinite, oops, sorry. Oh my goodness, okay, sorry about that. An infinite binary tree, and which is hyperbolic and non-amenable. And but let's say a less trivial example is actually a hyperbolic tessellation, which actually it's nicer to think of this kind of setting because it makes our results much more interesting. Let's say, obviously they work on the tree as well, but it's a very particular setting. Right. So what did we prove in this setting? Well, if we let G be an infinite hyperbolic and non-amenable graph, and we also need vertex transitivity, meaning that, so roughly speaking, vertex transitive graph means that every vertex has the same role in the graph. But a little bit more formally, so you can say that there is an automorphism from the graph to itself that maps the root of the graph or the origin or whatever your reference point is to any vertex of the graph, preserving the relationship of neighborhood. So we also assume the graph to be of bounded degree. Then what we show is the following. So the first point that we show is that for every value of lambda, so it doesn't matter how fast or how slowly the red process spreads, for all p small enough, so when the initial density of seeds is small enough, then FPP1 survives with positive probability. And this is already a big difference between what happened on ZD and what happens here. So here we have that this result, so FPP1 can survive with positive probability for all lambda, whereas in the other case, lambda had to be strictly smaller than 1. The second big difference is actually given by this second point here that we prove, which is the following. So for all lambda, again, for all values of lambda, and for all initial density of seeds, p between 0 and 1, FPP lambda, so the black process, survives almost surely. So this is a very striking result if you think about it, because saying for all lambda means it doesn't matter how quickly or how slowly the red process actually spreads. And by saying for all values of p, you are saying it doesn't matter how rare the initial seeds are, then what you are going to have is that FPP lambda is going to, with probability 1, is going to occupy an infinite connected component in the graph when time goes to infinity. And as a corollary of the first 2 points, we're actually getting that when the condition basically, since FPP lambda survives with probability 1, no matter what lambda in P is, then whenever we're in the range for FPP1 surviving with positive probability, then obviously we're going to have that FPP1 and FPP lambda both survive with positive probability. So they both coexist. Okay, is this result clear, or is there any question about it? Okay, it doesn't seem so. Yeah, there is a question maybe in the chat. What means small enough? Oh, that's a good question. So sorry. Actually, what happens is what you fix. So for any value of lambda, so you fix lambda, and you can say that there is a P0 positive. so that for every p smaller than p0, where p0 depends on the graph and on lambda, then this thing is true. P small enough means that. So there is some sort of, first you fix everything else, then you say, okay, there is a critical value, a p0, so that for all values below that one, this actually holds. FPP1 survives with positive probability. It is, well, we don't have explicit computations. I don't know if I'm just trying to guess the question, whether the question was actually asking for more information. So we do not have specific computations on the values of P0, but because sometimes we need arguments coming from percolation and things like this. So you can just say there is a value so that everything, so that for all P smaller than that value, everything actually works. But we don't have any explicit bound if that was part of the question. I don't know. Let me see. Okay, sure.
Could I also ask a quick question?
Sure.
So do you expect part one to be sharp in the sense that for P sufficiently large, FPP1 does not survive almost surely?
That is correct. Yes, I was going to say this in the next slide. Actually, yeah, maybe I'll get to this point exactly in the next slide, because
okay,
I mean there is quite a simple sort of way to see this. But okay, I'll comment on this in the next slide. Sure. Right. So I don't want really to discuss too much of the proofs of these results. I mean, I don't want to discuss the proofs of these, because today I would like to focus on another point related to this process, which is monotonicity. So I hope that in the previous slides, I managed to convince you that, well, okay, sorry. So at least I hope I managed to convince you that for at least lambda and p small enough, then FPP1 can survive with positive probability. On the other hand, which is basically answering the question that I got, it turns out essentially by percolation arguments that if P is too close to 1, then FPP1 does not survive almost surely. And basically the main idea behind this is it's very simple, because so you start with the density of seeds. So if you look at the vertices of the graph, which are not occupied at the beginning, which happens for every vertex independently with probability 1 minus p. Yes. The idea is if 1 minus p is below the threshold for percolation, then what's going to happen is that you are going to get that the area, the set of how can I say, the regions which are not occupied at the beginning are all finite just by percolation. So if 1 minus p is too small, meaning, for example, smaller than the percolation threshold, then all the regions which do not contain seeds are finite almost surely, which means that at the very beginning, the origin, which is where your black particle is standing, it will be almost surely confined within a finite region, which means automatically FPP1 is not going to survive, just because it cannot go further all the seeds. Does that make sense?
Yes, thanks.
Okay, sure, thank you. Okay, so as I said, so at least for small lambda, what happens is, well, if p is too close to 1, then FPP1 does not survive. In the cases that we know, well, if p is small, at least if it's small enough, then FPP1 has some chances of survival. Moreover, if you think about it, then, well, you can believe that if I add more seeds in the graph, then what's going to happen is that the seeds are going to get in the way of FPP1 spreading, right? Because they can interrupt black paths. So the natural conjecture is that for at least small values of lambda, the function, I mean, this quantity, so the probability that FPP1 survives when the initial density of seeds is p, one can think it's a monotone function in p. However, this is in general not true. And to disprove this conjecture, what we do is actually finding to construct an explicit graph G, which happens to be hyperbolic and non-amenable, and also quasi-transitive, but I'm not going to get into that. Such that when lambda is small enough, meaning for all small enough values of lambda, we can find two values, P1 and P2, where P1 is strictly less than P2, such that when the initial density of seeds is P1, which is the smallest value, the probability that FPP1 survives is actually 0. Whereas when the initial density of seeds is P2, which is the larger one, then the probability that FPP1 survives is strictly positive. So this is an extremely counterintuitive result, if you think about it, because I'm saying we can construct a graph where by adding seeds, by increasing the density of seeds, so I'm adding seeds, actually is helping FPP1 to survive. This is what we prove. Okay, and as I said, it's quite a counterintuitive result. So I would like to give in the next, in the remaining time, I would actually like to give you an overview of the proof, of the main idea of the proof. Unless you want to stop me now to ask some questions about the result. Okay, doesn't seem so. Right, so as I said before, what we do is we actually we say there is an infinite graph G, meaning we actually construct explicitly the graph G. And what we do is we start from, we start from a finite graph, which we call a tile. Okay, so this graph, maybe I'll go into details later on, but first I would like to give you an overview of the idea. So this tile here has a, a starting point, let's say, which is O, and an ending point, let's say, which is B, and it's naturally split into two parts, which are the lower part here and the upper part here, which are very well separated. They do not communicate. So the trick here is that whatever happens in the lower part is independent of what happens in the upper part. So this is going to be very important in the proof itself. However, we construct this kind of tiles, okay, we look at the following events. So what we actually do is we can find two values, P1, which is a value which is strictly between 0 and 1/2. Actually, P1 is quite small. And P2, which is a value which is strictly between 1/2 and 1, actually not too close to 1, to be honest. So these two values are very well separated. So that on the tile, the following happens. If we look at the event, the vertex B, which is the ending vertex of the tile, is infected by FPP1. What I mean by this is I let FPP1 start from here. I place seeds around on the vertices of this thing that I haven't really described to you yet. I place seeds with the density P. In the first case, we consider P equal to P1. So the probability that with this process, with FPP1 starting from here, the probability that B is infected by FPP1 first, meaning before FPP lambda reaches B, is smaller than 1 over capital N, where capital N is some very large integer. So this happens when the density of seeds is P1. If we consider the probability of the very same event, but with the initial density of seeds equal to P2, which is the larger value, then this probability, it comes out of the computation that this probability is actually strictly larger than 1 over n. So in the first case, it is smaller than 1 over n. The second case is larger than 1 over n. Okay, so this is something we find on the tile. Then what do? I said we take the tile and we construct a graph. So what we do is the following thing. So we take an infinite, okay, so this is just a picture of what it might look like, but think of the following. So you take an infinite tree, homogeneous tree with degree n+1, when n is exactly this guy here. So if you take an infinite tree with degree n+1, then the next step is you take every edge of the tree and you replace it by a copy of the tile that I showed you before. So the tile is this guy. And in particular, you place the tile as follows. So you take, you place O to be the vertex of the tile, which is closest to the root. And B is going to be like the final, so the ending vertex of the tile, so which is the furthest away from the root. So on one edge of the, so every edge of the tree is going to be replaced by this guy here. Then, so you're going to, okay, so since the tree was infinite, you have to imagine you are going to get something like this, but you know, an infinite version of it, where n is actually a very large number. So the degree is actually very large. Here I just put 3, but obviously it's much, much more. And what you do next is the following. So consider every copy of the tile inside the tree. And what you do is, in one, okay, so consider just the case P equal to P1. So consider this value P1 hat, which is the probability of the event B, the ending vertex of the tile, is infected by FPP1 when the initial density of seeds is P1. So what you do is you color every copy of the tile independently black with probability P1 hat. And with probability 1 minus P1 hat, you color it red. So why do we do this? So it's so if you think about it, so you color it. So the idea is to see. So the idea is to check if you, in the tree you are going to obtain an infinite black cluster containing the root with positive probability or not. So why do we want to do that? Well, if we get that there is an infinite connected black cluster containing the root in this setting here, then it means that this event here is percolating when the initial density of seeds is this one. So the thing is, when P is equal to P1, then the percolation, sorry, the rate at which I color each copy of the tile here is P1 hat, which, as we said, is strictly smaller than 1 over n. So what happens here is that when the initial density of seeds is P1, then the probability of coloring a copy of the tile black is strictly smaller than 1 over n. But 1 over n is exactly the percolation threshold for the tree, or degree n+1. So automatically you get that since this probability is smaller than the critical probability of percolation, then the probability that there exists an infinite black cluster here is actually 0. So there is no way that in this case you are going to get that FPP1 survives, because the event that I mentioned before does not percolate. So, and obviously we need this event to percolate in order for FPP1 to survive, because B infected by FPP1 just means, let me go back to the tile, just means that if I start FPP1 here, I occupy B by FPP1. So I can get to the next copies of the tile with FPP1. So this is the idea. On the other hand, if you take the initial seed, the initial density of seeds is exactly P2, then the probability of the event B is infected by FPP1 when the initial density of seeds is P2 is then P2 hat, which is, as we said, strictly larger than 1 over n. And by performing the same, you know, by doing basically the same thing on a different copy of this graph, we get that the percolation of the probability of getting a black edge, meaning a black copy of the tile, is strictly larger than 1 over n. And since it is, this probability is larger than the percolation threshold here, we get that here I meant to say there is an infinite black cluster containing the origin. An infinite black cluster, you're going to get it somewhere with probability 1. But what I meant to say here is that the probability that there is an infinite black cluster containing the origin is strictly positive. So meaning that the event I mentioned before is going to percolate. So there is a positive probability that the FPP1 process is going to survive forever. And I don't know exactly how I'm doing with time. So I mean, I see the time, but I don't know if you're still curious to see some more material. I still have a couple of slides, but just let me know what's more convenient. So I could stop here. So just let me know.
Okay, thanks. Well, we still have some time left indeed. Maybe this could be an opportunity for people to ask some questions, and then if not, then it would be, I think we would like to see the more material below.
Elisabetta?
So,
Yes.
Hi.
Hi, Wolfgang. Hi.
Hi. If I understood correctly, the graph which you construct is far from being transitive or quasi-transitive.
That's
what
correct.
What happens in the transitive case?
Okay, in the transitive case, we don't know. And in fact, it's a very bad thing that we don't know, because that would be obviously the most interesting setting, obviously, because most of this research has been done in vertex transitive case. So it's a very natural question. So the answer is we really don't know. We believe that some kind of monotonicity might hold in that case, but we have no idea how to prove it. So it's a bit of a sad issue. But yeah, so yeah, it's a very good question. Yeah.
Nobody asks one more. So you have non-amenability and hyperbolicity.
That's right, yes.
You might look as a toy example where you have non-amenability and only a little bit of hyperbolicity taken in a product of a tree with a line. It's no more hyperbolic.
Which kind of product you mean?
The Cartesian product of a regular tree with a line.
We have we don't know about that one.
Yeah.
What we know is that, for example, our results, so the ones I showed about the survival or coexistence kind of issue, we know that our results also apply, for example, to free products of groups, also when the factors are not are lattices, for example, or anyway, this object is definitely not hyperbolic, but we didn't manage to go much further than that. So we do believe that hyperbolicity is actually a sort of, I mean, we obviously used it massively for the proofs, but we believe that our results should be true also in the you know, when you just assume non-amenability without hyperbolicity, but we didn't manage to prove it. Thanks. I see there is someone in the chat. Is it possible?
Okay, I have a question, please.
Yes. Okay, then I'll go to the chat later. Yes.
Yes,
Sorry.
thank you very much for your talk.
Thanks.
Could you explain how you construct the tile?
Oh yeah, yes, okay, that would be in the next material, so in the extra material. Yes, okay, I will do it then. I will do it. Yes. I was trying to see the chat. There was another question. Is it possible to combine this with this SIR, susceptible effect remove process people have done with? I think Tom is a better person to ask this question to. So I'm afraid I will have to divert this question to the next talk, if that's okay. So I guess I'll let Tom. Yeah, perfect. So yeah, Tom is already answering. It's in the chat. Yeah, so I don't know if there are any more questions. Otherwise, I can just quickly expose. Sorry. Okay, yeah. If there are no more questions, actually, maybe I can quickly comment on the extra material where I actually explain how we construct the tile. If I don't know, tell me if that's okay.
Yes, we have time, so I think that should be okay. Yeah.
Okay, good. If I'm going over time, just don't hesitate to let me know. Okay.
Thanks.
Okay, so I'll back to the tile. So basically, this is sort of the crucial question, because the tile is actually where the magic appears in some sense, where the magic happens, if you want. So what do we do? So here, first of all, recall that this whole construction makes sense, and our results actually work for lambda small enough. So for all lambdas smaller than some critical parameter. Okay, so lambda is very small, meaning the red process is actually spreading very slowly. Right, so how do we construct the tile? As I said, this tile is actually naturally divided into two parts which do not communicate. So the upper part and the lower part. So this goes like this. So you start from the origin of the tile, and to construct the upper part, you just attach one edge which goes up. And then in the upper part, so what you attach to this new vertex, this end vertex that you just obtained, you attach a very long tree of degree d, where d is extremely large, is a very, very large number. So which just has to come out of the computation, but it's supposed to be a very large integer. So anyway, you get a tree which has very large degree, and it's very long. So it has a height which is some value L, which is another very large number. And once you reach height L, the next thing you do is actually you identify the next generation of the tree into one vertex only, which is this W up. And then what you do is you attach one more edge, and the end point of this edge is going to be vertex B, which is the end point of the tile. Regarding the lower part, what is happening is you start from O again, then you attach one edge going down, and at the end, at the next end point, you attach another tree, which this time is going to be a binary tree, okay? And it has some length h, okay, which is I guess it's small. I mean, I guess it's smaller than L. Anyway, you get this new tree here. Once you reach height h, then again you identify all the vertices in the next generation. The vertices in the next generation, you identify them into one vertex only, which is your W low. And then what you do is you connect this W low to B via a very long path. Okay, this is just a path of very long length. So this is what the tile looks like. And let me see if, okay, maybe it's better if I just tell you the magic, just, commenting on the picture. So what happens is the following. Suppose that you're looking at the case of the initial density of seeds P equal to P1, which is the smaller density of seeds. So P1 is actually very small for this to be easier. So it's very small. So what happens is, well, here you place your black particle, your FPP, the black particle is the one that gives rise to FPP1. And then for all other vertices in this graph, in the tile, you place seeds with probability P1, which is small. So what's going to happen is the following. So you have your initial configuration and you let FPP1 starts from here. Then, well, it will start spreading through these two edges, and FPP1 spreads at rate 1, recall that. And then what happens is, at some point, you will get to this, entering this tree and also entering this tree. So since P1 is very small, then it's very likely that there are going to be plenty of paths going from O low to W low inside this tree, which do not cross seeds. Because when P1 is very small, then the probability, the critical value for the probability of percolation, critical probability for percolation for example, in the binary tree is 1/2. So if P is much smaller than that, then it's very likely that you're gonna have a lot of paths going around here that join O low to W low, which do not cross seeds. And the same thing happens in the upper part here, in this upper tree, because it has degree D, which is much larger than 2. As I said, P is very small. So again, it's very likely that there are going to be lots of paths going from here to W up without crossing seeds. So what happens here? well, FPP1, let's consider the lower part. So FPP1 starts from here, will spread around here, and will start going around, this, making its way through the binary tree. Well, it will take it a while, but then at some point it might cross some seeds, but it doesn't matter because there are plenty of other paths they can take. So it will go around this, will take paths that do not involve seeds, and then it will reach this point. In the meanwhile, since this guy has a very, very long height, then, well, FPP1 is also going to be very likely to reach W up, but it's going to take a long time to do that. So what is likely to be happening here is that by the construction of this tile is that W low is going to be, it's very likely that W low is going to be infected much, much quicker by FPP1 than W up. Because when W low is infected, FPP1 has so much road to do, so many edges to cross, that it's going to take a while. So here it's going to be a bit delayed simply because this guy here is very, very big. So, okay, so we get FPP1 here, while on the upper part it's still fighting to get through. And as I said, from W low to B, we have a very long path. Since the path is very long and the density of seed is positive, then it's very likely that at some point on this path there is going to be a seed. So as soon as FPP1, which is quite quick, meets the seed, then from that point on, the process is doomed in the lower part to be just FPP lambda because it has no way to escape. So FPP lambda will start spreading. It will be very slow, but it doesn't matter because FPP1 will take a long time to make its way through here because this tree here is extremely big. So this is why it's very likely that what's going to happen is that FPP lambda is going to arrive here first, while FPP1 is still going to make its way through here. So the main idea is that the small density of seeds here was crucial in order to make FPP1 move very quickly through this lower tree, in order to give a push to FPP lambda and in order to let it arrive here first. On the other hand, which is one other slide, but I guess I'll still comment on the picture. On the other hand, when the density of seeds is larger, in particular larger than half, then it's very likely that here, so since it's larger than a half, which is the critical probability for obtaining a percolation in the binary tree, so since it's larger than a half, it's likely that all paths joining O low to W low are going to, inside this tree, are actually going to meet seeds. Whereas since here D is extremely large, it's likely that there will still be a lot of paths joining O up to W up, which inside this tree, which do not cross any seeds. So basically, if you consider this second setting, what is going to happen is, okay, you start your FPP1 from here. It's going to spread above and below. And well, above, what is going to happen is quite similar to what was happening before, because FPP1 is likely to find its way up to W up to the end. However, in the lower part, things are really changing here, because since it's likely that we are going to get seeds obstructing the way, all the ways that lead to the end of the tree, what's going to happen is that FPP1 is going to proceed as FPP1 for some time, but then eventually all the paths are going to give rise to some FPP lambda process. But FPP lambda is very, very slow because lambda is small. So here you're going to create a huge delay that is so large that it will still give a lot of time to FPP1 above to actually reach W up and eventually infect B, and before FPP lambda comes from below. So this is sort of where the magic happens. And I guess, well, this is actually what I told you, and now I am done, and I don't have any extra material. And of course, if you have any questions, just ask. Thank you.
Okay, thanks very much. Are there any other questions for Elisabetta?
Okay, something in the chat.
Yes. It was
Okay.
very clear.
Well, thank you. Thank
I
you
agree.
for listening.
May I indeed ask one more question?
Yes.
Thank you. I'm just interested, I mean, some of the relationships you described for lambda and for peace were somewhat inexact. You mentioned monotonicity during the talk. Are there any more specific results here? Say exact limits, exact relationships, and so on. Say for kind of phase transition that you have shown, and so on. When do the things exactly happen? Those results.
I'm not entirely sure I got the question. Sometimes I couldn't hear very well. So sorry, the
yes.
relation between, I'm sorry.
Yeah, do you hear me? Yes.
Yeah. It just
sorry.
Sometimes maybe it's my connection, I don't know, but please, sorry, can you repeat that?
Thanks. So are any more exact results on when do the phenomena that you described happen for P's and for lambdas available? To mention monotonicity and similar things.
For P's and for lambda, but you mean if we have if there are any explicit values found for this?
Bounds for, yes, values you mentioned, true.
That's a difficult question. So in our case, we do not, I mean, in the papers that we have, we do not really compute any specific value. So we just say, also because, as we said, sometimes we do need tools from, like, for example, for results from percolation. So you just know that in some cases, you just know, okay, there is a critical value where this happens. Well, in the case, for example, trees, then it's okay, but for general graphs, it might be a bit more difficult. And so or for some phenomena like this, you just know that there is some critical value where you get a phase transition, and we use that, we say, okay, since there is that value, then we can find another critical value where something happens. But we normally we did not compute anything specific, also because sometimes it's just not possible. I'm not really aware of any exact values for this kind of phase transitions also in other papers. I just think one can say, oh, there is a value for which this and that happens, but I'm not aware of anything more specific.
Okay. Thank you.
Sorry.
Thanks.
No problem.
Thanks.
Okay, are there any other final questions? Okay, if not, let's thank Elisabetta again for the very nice talk.
Thank you so much. Thanks a lot.
Thanks very much. So we'll take just a 2-minute break, and we'll resume back at 1 minute past 3 with Tom's talk. Thanks.
Hey, Tom, maybe we can try to see that your screen sharing is working.
Okay, I'll just try and get it up. Just 1 second.
Okay. No problem.
Can you see my slides?
I only see
No,
the
actually.
full bar or something like that.
Oh, okay.
Yeah.
Okay, 1 second.
Okay, great. Welcome back. So our second speaker today is Thomas Sven from Durham University, who will be speaking to us about coexistence and competing first passage percolation part 2, non-equilibrium multiscale analysis. Okay, so over to you, Tom.
Oh yeah, thanks for the invitation to speak today. Thanks everyone for coming, and thanks Elisabetta for the first half. So today I'll be speaking about joint work with Alexander Stauffer that looks at competing first passage percolation, but we're going to have a particular focus on results on the lattice. So perhaps I can talk about the model very quickly, just in case anybody's turned up, just for the second talk. So remember that we have FVP1, it starts at the origin. So in our case, we'll always be on the lattice on ZD for D bigger than 1. It spreads to the edges of the lattice of 8,1. And we also have seeds that we place on each side with probability P. When we get to a seed, we activate it, and then FVP lambda starts to spread from that seed at rate lambda. So we've got these two parameters, P and lambda. So the evolution might look like this, and we're interested in whether FVP1 survives or FVP lambda survives, or whether they can coexist and survive simultaneously. So here survival is the emergence of an infinite connected component. So FVP lambda always occupies infinitely many sites because there's infinitely many seeds, but the question is whether or not that component is connected, or if there is any connected components. Okay, so hopefully the model's clear, even if you just showed up. So just to reiterate simulations, so I think this was in Elisabetta's talk as well, we want to understand the geometry of sites occupied by FVP1 and sites occupied by FVP lambda. So here the colored region is sites occupied by FVP1, and the white region is sites occupied by FVP lambda. So here FVP lambda occupies large regions, but FVP1 still seems to be sustaining itself. So if we look on the boundary, it seems that FVP lambda is occupying enough sites that it might survive. And even in this picture, it's unclear whether or not FVP1 survives, FVP lambda survives, or whether they could survive simultaneously. So the question we'd like to ask is, can we prove if there's a regime where both processes survive simultaneously? And just to give another picture, so in this previous picture, the density of seeds was very small, but lambda was quite large, so it was quite close to 1. But in this picture, the density of seeds is quite large, but lambda is tiny. So here now, FVP1 can propagate well, but it has to navigate around quite a large density of seeds. Whereas there's many seeds, but FVP lambda propagates very slowly. So here the balance between FVP1 and FVP lambda is a bit different. So we see that the geometry of the clusters is quite different. So in this picture, we see quite a ramified structure for FVP1. So it appears to have some self-similar properties. Whereas here, FVP1 looks like a large percolation cluster. So the question is, we have two different regimes where P can be large and lambda small, or P can be small and lambda large. What can we say about the survival in these two different regimes? And as Elisabetta proved in the last talk, that it's quite hard to analyze this model. So FPPHE kind of resists any easy arguments because of this lack of monotonicity. So this diagram here is a bit of a cartoon where by adding a seed, which is a small pink circle, we delay the activation of a larger component of seeds, which may benefit FPP1 because we delay the activation of a big component, and in that delayed time, FPP1 can travel around and encapsulate it. So in general, there's no easy argument that says if I increase P or increase lambda, then I know that I'll occupy more or less sites with either process. So this is quite a subtle feature of FPPHE, but it really prevents being able to say anything immediately. We have to work quite hard to say anything. If there's any questions in the chat, I don't think I can see, so please let me know. And is there any questions at the moment? So this is kind of a recap. So far, is everybody happy? Okay. So what can we say about FPPHE on the lattice? So as mentioned in Elisabetta's talk, the first result for FPPHE was saying that we get the so-called strong survival, where as long as FPP lambda is slower, as long as P is small enough, FPP1 will survive and FPP lambda does not. So to be precise, FPP1 will occupy an infinite connected component, and all the components of FPP lambda will be finite. And this is an event of positive probability. So the proof for this is quite an involved multi-scale analysis where you control the process by setting P very small and controlling the spread of FPP lambda from these seeds. The question is, can we flip it around and say, for all P below a certain value, if lambda is small enough, do we always get survival? And this is our main result from our work, which says, again, as long as dimension is bigger than 1, because in dimension 1, the model isn't very interesting, as long as P is less than 1 minus PC site, which I'll explain in a second. So as long as P is less than this specific value, as long as lambda is small enough, we get that FPP1 survives with positive probability. So the thing to note is that if P is bigger than 1 minus PC site, where PC site is a critical probability for site percolation on ZD, then all the connected components of non-seeds are finite. So if P is bigger than 1 minus PC site, FPP1 could never survive. So we're saying that as long as there's a positive probability that the origin is in an infinite connected component of non-seed sites, then FPP1 has a positive probability to survive. So really our result goes as far as you can go for the density of seeds. So as long as there is a path to infinity, as long as lambda is small enough, so as long as FPP lambda moves slow enough, you can survive. And you might be able to preempt how we get coexistence here. So that if we can choose P so that both non-seeds and seeds percolate, then we get a coexistence regime. So if the dimension is bigger than 2, and P is between PC site and 1 minus PC site, then there is a infinite connected component of seeds and an infinite connected component of non-seeds. So from our theorem, if lambda is small enough, then we get coexistence with positive probability. So this won't work in dimension 2 because PC site is bigger than 1/2 in dimension 2, but it's known that PC site is less than 1/2 in dimensions 3 and higher. So this is our main result, that there is this regime of coexistence on the lattice for these values of P and lambda. So the natural question is, can we prove this on Z2? And can we prove it for all P, even for P where seeds don't percolate to time 0? And these are very difficult problems. So there's not much progress that's been made on these two open problems. So if we go back to the simulation, so saying whether or not there's coexistence in this case on the lattice for dimension 2 is a very difficult open problem. So those are the main results. Are they clear? Are there any questions about our main results? Okay, if not, so for the remainder of the talk, I hope I can go into a bit of a deep dive about how we proved this. So recall our result says that on the lattice, I think I see a question in the chat. Oh, sorry. So I might have brushed over PC site. So PC site, so that's a critical probability for site percolation on CD. So if P is bigger than PC site, there's an infinite connected component of seeds, almost surely. If P is smaller than PC site, then all connected components of seeds are finite. Okay. So thanks for asking. Okay. So yeah, so our main result is this. If the dimension is higher than 1 and P is less than 1 minus PC site, in other words, if there's a chance that FPP1 can survive, then as long as lambda is small enough, it will survive with positive probability. And our proof is split into 2 steps. The first step is a multi-scale analysis, which I'll call in equilibrium. So this is where I tessellate the lattice for the boxes, which will be done at infinitely many scales. And I'll label those boxes as good or bad according to local events. So I'll look at the distribution of seeds in the box and the distribution of passage times in the box. And I'll want to show that there's a notion of good that occurs with high probability that will be beneficial to us. And the second element is a feedback structure. And this is because this model is non-equilibrium. So it doesn't matter how good a local region is, I'll potentially have to observe the entire process to understand if FPP1 survives or not. Because it doesn't matter how beneficial a region is to FPP1, it could be the case that FPP lambda arrives first, and it ruins the goodness of that box. So we'll have to build a feedback structure that can take advantage of these good local events. So this is a very high-level description. I'll get into the details in a moment. And to make this description a bit nicer, we'll actually prove a simplified version of our main result. So we'll actually prove that by setting lambda and p small simultaneously, that we can show that FPP1 survives with positive probability. So the reason I'm doing this is to, A, I don't have to introduce lots of events concerning supercritical percolation, and B is that the proof is essentially the same. So I can discuss the proof for this in this simplified case, and to supercharge it to the full case, it is quite immediate. So I'm going to talk about the simplified case first. So what is step 1? So what is this initial multi-scale analysis? So the event I'm going to look at is as follows. So I'm going to tessellate the lattice with these scale 1 boxes. So these are boxes that have side length L1, where L1 is some large constant. And the first thing I say is it can't contain seeds. So I'm going to set P so small that once L1 is fixed, this box contains no seeds. The second part is that between any 2 sites inside the box, FPP1 the time it takes for FPP1 to travel to those sites using just FPP1 passage times is bounded above by some constant times L1. Again, you can play with this constant. And the last thing is that the FPP lambda passage time on any edge inside of B is greater than, let's say, some constant L1 all squared. And if a box is not good, then it's bad. And the thing to note is that we can set the probability of a box being good arbitrarily large once C and L1 are fixed by setting lambda and P sufficiently small. So there's a notion of good localness such that if FPP1 gets to a box first, it will occupy everything inside the box, potentially except the boundary. Because if FPP1 has already arrived to the boundary of the box, it's able to travel everywhere before FPP lambda can even propagate across a single edge. So this seems good, that I tessellate the lattice with these overlapping boxes. They occur with high probability, so if this probability is high enough, they will percolate. But there's a big problem here, which is I don't know that FPP1 is going to arrive to a good box first or not. If FPP lambda enters the box first, then there's no use to the goodness anymore. I won't be able to guarantee that FPP1 can spread inside it. And this is a problem because I can't estimate the probability that FPP1 arrives to a box first. I have to observe the entire process potentially to guarantee this. So I can't just analyze this process with local events. Somehow I need to incorporate the entire history of the process to analyze it. So how do we do this? Well, I'm going to further classify good boxes as follows. If FPP1 gets to a good box first, then I'll say that's positive feedback. And similarly, if FPP lambda arrives first, it's got negative feedback. So on the surface, it doesn't seem like I've done a lot. I've just introduced a definition. But the utility of this is that I'm going to analyze the consequences of positive feedback and the consequences of negative feedback. The consequence of positive feedback is that if FPP1 arrives first, it will take advantage of the goodness of the box and occupy all the sites inside it that aren't on the boundary. But what about negative feedback? Well, suppose you have a good box, but FPP lambda arrives there first. So this gives it negative feedback. And you ask, why did it have negative feedback? What happened? So you say that, well, FPP lambda propagated to the box. So there must be a neighboring box that FPP lambda propagated it to it from. And I ask, well, why did that happen? And the idea is that where you first enter from the box, you can associate a neighboring box and call it, say, the parent. And the parent of a box that has negative feedback can't be a positive feedback, because a positive feedback box wouldn't allow FPP lambda to propagate. So if a box has negative feedback, its parent must have negative feedback or be a bad box. So you keep going backwards in time from a negative feedback box until you get to a bad box. And this bad box, you can say, causes the negative feedback. And the idea here is that it's very slow for FPP lambda to propagate through good boxes. So the spread of negative feedback from bad boxes is going to be quite slow. And the slowness of this negative feedback will allow positive feedback to surround it. So this is a main idea of this non-equilibrium feedback structure. So again, we're not estimating the probability that a box has positive feedback or negative feedback. We're looking at the consequences of what happens if they have either. And so this picture shows what happens, say, where on the left, you have bad boxes that are far from one another. So if FPP1 arrives near this box, then it's able to spread around it quickly and encapsulate its effect, because FPP lambda moves so slowly that I can't control what's happening inside the bad box, but I know FPP lambda is slow through good boxes. So the FPP1 is able to go near the box and spread around it. So the effect of this bad box will be encapsulated. And if every bad box was far from one another, then I would control the spread of FPP lambda. The issue is that we must encounter arbitrarily large regions of badness. So on the right, we have that FPP1 approaches a large cluster of bad boxes, and it's not able to encapsulate it before the spread of FBP lambda can infect another bad box that looks like it should be controllable, but it's not. So we're able to control bad boxes as long as they're far apart from one another, but how can we control these arbitrarily large bad regions? So the idea is to kick in a multi-scale argument. So good and bad boxes at scale 1 are defined with local events according to the distribution of seeds and the distribution of the passage times. And we define good boxes inductively. So a scale K box is good if it contains no more than a certain number of disjoint bad boxes at scale K-1. So to assess if a region is good or not at scale K, I look inside the geometry of the bad boxes at lower scale. So if there's only a constant number of disjoint bad boxes, this tells me that the hope is that these lower scale bad boxes are controllable at scale K. And a very common calculation in multi-scale analyses is saying that, well, the probability that a scale K box is bad decays exponentially in the probability that, or more than exponentially, in the probability that a scale 1 box is bad. So the probability you get a large region that is bad is very small. So the aim now is to systematically control arbitrarily large regions of bad boxes by looking at a large enough region where that region can be controlled. And because the decay on the probability that a scale K box is bad in K, that this probability will be summable. So eventually you're going to reach a scale where any region is controllable. So now we're going to have to implement positive and negative feedback at each scale. So how do we do this? So I hope that this definition isn't too confusing. I'm happy to try and explain it. But it's going to be inductively. So first, I'll go to scale 2. So I'll say a scale 2 box has positive feedback. A scale away from the boundary, such that when that positive feedback box is entered for the first time, it's not too much longer after when the bigger boxes or the scale 2 box is entered for the first time. So the idea is that when either process enters a scale 2 box for the first time, then you expect to see a positive feedback box away from the boundary in a sufficiently fast time. The idea is that, there's something in the chat. Yes. Okay, so this is important, so I'll try to go over this in detail. So what does it mean to have positive feedback at scale 2? Is that the idea is that FBP1 enters the box and it's able to get away from the boundary. So it's able to enter this dashed region, which is some small constant times the length of the box, in a time that it is what you would expect for the rate 1 passage times to C. So the reason we have to encounter these difficulties is that FBP1 could enter a bad box near the boundary. But the idea is that it should be able to encapsulate it and enter this inner region. So if you don't like this definition, the idea to have in mind is just that FBP1 enters the box well and is able to spread to the center. So this is what it means to have positive feedback, that FBP1 is spreading like you expect it to. So it might encounter bad boxes, but it's able to spread around them. And what I would like to prove that I have as a statement here, but it requires a proof, is that if a scale 2 box has positive feedback, so that, you know, there's a positive feedback 1 box inside this inner part in a nice time, then every box that's not close to a bad box in this inner region will have positive feedback. So this is similar to a scale 1, where I'm saying if FPP1 enters a box, then it conquers everything inside the box. At scale 2, I allow for some badness inside the box. You just have to. You can't control the probability of a scale K box being good very well if you demand everything inside is good. The badness gives you some leeway. But now the issue is that I can't conquer these bad regions. What I would like to say is that I can conquer everything that's not close to these bad regions. So how would you prove this? And this proof is really the heart of the paper. Because if you can prove it from scale 1 to scale 2, then you can prove it inductively from scale 2 to scale 3, from scale 3 to scale 4, and so on. The difficult part is defining positive and negative feedback at each scale, and that all the nice properties hold. So let's approach it by contradiction. So what if there was a negative feedback scale 1 box inside the scale 2 box away from a bad box? So in this uppermost bad box, this red arrow leaving this dotted region is representing negative feedback spreading quite far. And the question is, why did this happen? So I know at scale 1, I'll be able to encapsulate bad boxes that are well separated. So the encapsulation of this box failed. So why would it fail? It would fail because FPP lambda arrived there before FPP1 could. Because if it didn't, because I have positive feedback, I know FPP1 can spread there fast, and it would be able to encapsulate it. So this encapsulation has failed because FPP lambda was nearby. But how did FPP lambda get nearby? Well, it's because an encapsulation must have failed elsewhere in the box, or it spread from outside of the box. So if it spread from outside of the box, I'll worry about that later. If it failed because of another failed encapsulation, then the same applies. Why did this encapsulation fail? So you keep going backwards in time until you deduce that an encapsulation failed because negative feedback spread from outside of the box. But remember, it takes negative feedback a long time to spread because lambda is set to be very small. So the time it would have taken for negative feedback to spread inside the box, ruin all these encapsulations, this is much larger than the time it would take the positive feedback to spread inside the box anyway. So the idea is that if you have positive feedback, you're guaranteed to encapsulate everything before negative feedback is able to spread inside the box. And this is why we need a buffer region for this inner part, because we need there to be some distance that FPP lambda would need to cross to get inside the box. So what this shows is that at scale K, say, if I can show that positive feedback can spread well inside the box and negative feedback spreads slowly, then this consequence happens where if I have positive feedback, then everything in the box away from bad boxes must be taken. And the important thing to note is that I only care about the scale immediately lower. Because you could ask, well, what's happening at scale K minus 2? What's happening at scale K minus 3? And the idea is that you get this cascading property that at scale K, I don't care about K minus 2 because I would go to the scale K minus 1 boxes. But this cascading property says, well, the positive feedback guarantees that the lower scale boxes have positive feedback. So to go downwards in scales is quite immediate once you have this inductive property. And once you get to scale 1, this is where you're saying that the sites are occupied by FPP1. Okay, so just before I get to the final part, are there any questions about this kind of non-equilibrium multiscale part? Okay. So the question now is that with this framework in mind, where we have these local events that are good or bad, and we're analyzing them through this non-equilibrium feedback mechanism, how do we deduce our result? So the idea is that I look at every box that contains the origin. So there's infinitely many scales, and there'll be some constant number of boxes that will contain the origin at each scale. But because the probability that your bad is summable, there's a positive probability that all boxes at all scales that contain the origin are good. Oh, well, there's a positive probability that all boxes at all scales that contain the origin are good. I think in the paper we say that this is saying that the origin is wonderful. And because FBP1 is already active in these boxes, all these boxes have positive feedback. And because they all have positive feedback, it means if I fix any k, I guarantee that everything in the inner part of k will have positive feedback at scale k minus 1, which means each k minus 1 box has positive feedback at scale k minus, each k minus 2 box in each scale k minus 1 box will have positive feedback that's not too close to bad boxes, and this property cascades down to scale 1. And this shows that FBP1 survives at each scale, and it survives at every scale, so there must be the emergence of this infinite connected component. So from this, how do we prove the full version? Well, it's not just for, we can set p small, we can set p between 0 and 1 minus bc site. So all we have to do is change the local events. So what this involves is saying that, okay, I won't impose that there's no seeds, but what I'll impose is that the non-seeds percolate well inside the box. So I set L1 large enough so that the component of non-seeds is highly supercritical. And this allows FBP1 to spread. So this requires some technical events, but the principle is the same, and the non-equilibrium feedback runs through essentially the exact same. So this framework is quite robust to the choice of local events. As long as you can define positive and negative feedback at each scale, which requires quite a lot of work, but the principle is quite, the principle is the same at each scale. So that's essentially how we proved our main result. So are there any questions about that? Okay. So now I'm going to step away from FBPHE for a few moments. And I'm going to talk about its relationship with MDLA. So this was alluded to by Elisabetta. I'm going to describe how FBPHE isn't just an interesting model in its own right, but it's actually a very powerful tool. So what is MDLA? So it's this random aggregation model where there's two types of particles. So initially at time 0, you have a single aggregate particle, say at the origin of this lattice, say, and you place particles with density mu. So these are the red particles. And there's the exclusion rule, so that there's only one particle allowed at each site, at most. And the particles do a simple exclusion process, so random walks, where if there's only a particle there, then that movement is suppressed. But aggregate particles, the particles in black do not move. So the red particles move, the ones in black don't. And the evolution of the aggregate is where if a red particle attempts to jump onto an aggregate black particle, then that particle becomes an aggregate particle and is fixed there forever. So for example, the particle next to the aggregate here might attempt to jump onto the aggregate, and then it becomes black. So if we let this evolve, perhaps the aggregate looks like this after a certain time. And the question is, what does the aggregate look like after a long time? So understanding the geometry of MDLA is a very hard question. So this is a simulation from Sidoricius and Stauffer, where on the left, the density of particles initially is 0.1, and on the right, it's 0.3. So we seem to see quite a different behavior, where on the right, we're growing with the boundary seems to be quite well defined, but we still have a very complex structure internally. And on the left, we seem to have the emergence of these arms, and we're growing with less density. So the question is, can we say anything rigorous about this? Can we say what the boundary looks like? Can we say what speed the arms are going? And this is a very challenging model. And for a long time, essentially nothing was known. So what the breakthrough by Sidoricius and Stauffer established was that in any dimension bigger than 1, as long as mu is close to 1, or close enough to 1, then the aggregate grows linearly in time. So this is really like the first rigorous result for MDLA. There is a slightly different formulation where you have a Poisson density, and there's not exclusion. And this was analyzed by Alan Sly, but they prove similar results. But in this paper, they look at the simple exclusion process. So how do they prove this? So what does FPPHE have to do with this non-equilibrium particle system? Well, what makes MDLA so hard is that to understand how it evolves in time, you have to understand the geometry of the aggregate. But this is hard. It's hard to capture this information. The idea is that if mu is large, so if it's very close to 1, then you can imagine that basically every site is a particle. Once in a while, you get a site that doesn't have a particle. If every site has a particle, then the aggregate is growing like a first passage percolation process. So it's growing with, so it looks like an FPP ball. The problem is that eventually you get to a site that doesn't have a particle, and this slows you down. So what you do is you control the effect of these holes that causes a slowdown with a coupling that's very delicate with FPPHE. So FPP1 is like the aggregate behaving nicely, and FPP lambda is where you can't control the aggregate because of these holes. So by showing that FPP1 survives, you're showing that the aggregate is going linearly in time. So this is why Sidoricius and Stauffer introduced FPPHE. And it turns out that most of the paper was proving the strong survival regime. And then this delicate coupling with MDLA lets them establish this linear speed. So this was a breakthrough for MDLA, and it was facilitated by this coupling with FPPHE. And a similar breakthrough was made more recently by Dovern and Sly, where they look at the SIR model. So in this model, you take a Poisson cloud on the lattice, and each particle evolves as a simple random walk in continuous time of rate 1. And you place a single infected particle at time 0 at the origin. And the infected particle moves at rate 1 too, with the rule that if it occupies a site that contains another particle that's susceptible, it infects. But infected particles have a lifetime, and they recover at a certain rate. So Keston and Sidoricius proved that if this recovery rate is sufficiently large, then the infection dies out. And they could prove this because you can dominate it with a simpler model, the SIS model. But proving it survives for a small enough recovery rate was very hard. The reason is that this is also a non-equilibrium particle system, and because particles are dying, you're reducing the density. And it's also not monotone in any of its parameters. You could engineer situations where adding infected particles could kill you, because you might remove particles that could be super spreaders, say. So again, it was for a long time an open question to prove that you get survival if the recovery rate is small enough. So what Doven and Sly did is that they had a very ingenious construction of the model where they could construct it with IID blocks, where when the infection reaches a region of the lattice for the first time, you sample particles in that box, and then you let the infection spread through that. And it turns out that by generating this process, by generating these fresh regions, you can then couple that process with a streamlined version of FPPHE, which they call Sidervicius-Stauffer percolation. And so by doing this coupling, they control regions of the lattice where the infection is behaving well. So you could consider that positive feedback. And they can control regions where it's behaving badly. So where there's too few particles or where infected particles don't behave very well. And by encapsulating these bad regions, they actually can prove that the infection survives as long as the recovery rate is small enough. And actually, the techniques are so robust, they can prove a lot more. They actually prove that the infection spreads linearly, and it leaves behind a herd immunity regime, where there's actually inside this infection annulus, there's a density of particles that move through the infected region and avoid infections. So the infected region, that's this random annulus, defines a subcritical region where there's a low density of particles, and the supercritical region where the infection hasn't spread yet. So I hope that these descriptions have shown that FPPHE is a very powerful way to analyze these difficult non-equilibrium particle systems. And that all these three models, FPPHE, MDLA, the SIR model, the real goal is to control these bad regions that are defined locally. But to do this, you have to apply this non-equilibrium structure. And this can be done by this multi-scale argument, and it can be done by coupling with FPPHE directly. So I hope that this description has been clear, but if there's any questions, please feel free to ask.
Okay, thanks very much, Tom, for the very nice talk. Okay, so we had a couple of questions in the talk already, but are there any more questions for Tom? Maybe I have one. So you defined these this multi-scale analysis, these kind of good and bad boxes that appear in different scales.
Mm-hmm.
This seems like I don't know, to me it seems like quite a general idea in some sense, how to sort of advance from that kind of grow in size in terms of like much smaller events. Somehow similar ideas appeared in analysis of other models somewhere, or is this kind of quite unique to this, as far as you know, quite unique to this model?
So the multi-scale setup is very broad. So like the inequilibrium multi-scale argument is that's appeared in many, many models. So like Gaussian free field, random interlacements, percolation. But in those models, you almost always require monotonicity, because in many of those models, you would like to do these like sprinkling arguments where you can decouple boxes in space-time.
Mhm.
So you really require monotonicity in many of those models. But our model isn't monotone. So we have to use this non-equilibrium structure to that doesn't involve that.
Is this where the so if I understand correctly, is this where this feedback structure plays a role?
Yes, so we have these good and bad boxes that are local, defined with this multiscale, but the feedback structure controls the effect of bad boxes. So I want to say that most boxes are good and they have positive feedback. But doing this directly is quite hard. So what you have to prove is that if a box is good but behaves not as you expect, it's because of a bad box. And controlling it through this kind of lens lets you systematically eliminate the regions that are not behaving well.
Mm-hmm.
So in a standard multiscale argument, good and bad is sufficient. The difficulty is defining them in the right way.
Mm-hmm. Okay, interesting. Thanks.
Maybe can I ask just one very quick question?
Sure.
It's actually a question that I get a lot when I give a talk on this topic, and I do mention your result about coexistence on ZD. So since the case D equals 2 is still an open problem, what's your guess? Do you think you're gonna get coexistence or for some range of parameters, or what do you think?
If I were to guess, I would expect there not to be coexistence. Just because in 2 dimensions, it's difficult to see how there's space for both. But that's a very non-rigorous answer. But that's what I would expect. Proving it is hard.
I also have 2 questions, if I may.
Oh, sure.
Thank you. First one is maybe related to the very early question by Sergey about this finiteness of the process.
Okay.
What would happen if if you would have a lattice with only finite number of vertices? So if you would not have possibility to go infinite in dimension. And secondly, more general one, this is basically a random graph. Does anything of this depend on the topology of the graph? On the, say, how we define the geodesics, distances, and so on?
Okay, so the first question. Yeah, I guess we've only looked at it for infinite graphs, so I guess you'd like to say what could be said if you take just a box?
Yeah, just like interesting.
Yeah, so I guess like a natural question would be how much of the boundary would be taken by FPP1 and FPP lambda? Yeah, I've not thought about that. Perhaps like a lower bound on the number of particles that I think our results could probably show that. So our proof says that that FEP1 actually occupies a positive density of sites. And I think by setting lambda sufficiently small, you can get that FPP1 occupies essentially 1 minus theta p sites. So it's essentially occupying as many sites on the infinite cluster.
Mm-hmm.
So yeah, I would guess if you took yeah, but maybe there's other interesting questions in finite regions as well.
Sure.
So, yeah. And And the second question, which was
About the topology. So does anything of this used?
So I think our results are robust to kind of lattices dependent on kind of percolation estimates and if they all go through. So yeah, a lot of the events that we need are quite technical and kind of generalizing the statements would require like quite general statements about like chemical distance, so you can probably push it to other lattices, but the effort required might not justify it. But in terms of outside of the lattice, I'm not sure. Yeah. Yeah, I would have to probably think about what can be said outside these cases, but I think you.
Thanks. It was a great article. Thanks.
Well, thank you. Does the size of the boxes affect the result survival? Or does it not matter? Oh, sorry, I'm seeing the question in the chat. So as long as the boxes are sufficiently large, it won't matter, I think, because you have to fix it at scale 1, but you have to look at boxes at every scale. So you're going to have to look at boxes of arbitrarily large size in any case. So as long as your initial scale is large enough, then the machinery goes through. No, thank you.
Yes, indeed. Thanks for the talk. Are there any? We have time for another quick question for Tom. Okay, if there aren't any, let's thank Tom and Elisabetta again. Thank you both for the very nice talks.
Thank you.
And we resume with the seminar in 2 weeks from now. Thank you very much.
Thank you for having us.
Thanks.
Thanks a lot.
Thanks.
Thank you.